TF-23 KAAN. King of the Kings. Turkish Eagle. The most comprehensive project of the Turkish defense industry since its inception until today is the National Combat Aircraft, Turkish acronym, MMU, TF-23 KAAN. In the development of KAAN, it is aimed not only to produce domestic structural parts, but also to integrate domestic twin turbofan engine, domestic weapon systems, domestic avionics and sensors, AESA radar, EOTS, IRST, RWR, MWR, etc., and other components last, but not least domestic jet drones for the first time. This video includes details of technical explanation about KAAN 5th Gen fighter jet. Stealth and very low observable VLO fighter aircraft. Radar cross-section RCS of KAAN Block 1 was designed at -20 dB SQM, 0.01 square meters. We expressed this prediction in our previous article. The RCS value, -20 dB SQM, was confirmed also at the press day on June 30, 2021 of the Anatolian Eagle training held at the Turkish Air Force 3rd Main Jet Base Command between June 21 and July 2. Radar reflection techniques used on KAAN with comparison of 4th Gen. Creeping wave countermeasure. Diamond nose shape of KAAN. Rafale's nose allows creeping wave return to enemy radar antenna. Vertical stabilizer. KAAN has twin tilted stabilizer. Rafale has perpendicular stabilizer. Air inlet ducts. KAAN has S-routing duct to hide engine compressor blades from direct enemy radar signals. It can be estimated also RAM coating on inner surface of duct. Some portion of Rafale engine compressor blade can be seen directly from enemy radar signals, and echo returns to enemy radar antenna in front of Rafale. Nose antenna. KAAN's antenna, tilted. Rafale's antenna is perpendicular. Edge diffraction and traveling wave. KAAN's leading and trailing edges are reflective angular shaped. KAAN's radome connection edge to fuselage has sawtooth. Rafale's radome connection edge to fuselage and aft fuselage upper edge nozzle around are perpendicular, have no sawtooth also. Magnetic tape on sharp edges. Present on both KAAN and Rafale. Geometry of the KAAN has convenient countermeasures for radar stealth. Since internal weapon bays and internal fuel storage are designed, it is principally correct geometry. In addition, it is known that domestic RAM layer and radar signal domestic absorbing magnetic coating and paint will be used on surfaces that see radar signals. KAAN's radome sharp peripheral lines, air intake edges, front wing slat fuselage junction areas, wing leading and trailing edges, stabilizers are covered with a magnetic layer, tape, visible in yellow and black in the photographs. It is aimed to reduce the radar signals that are directly reflected via edge diffraction and that travel to the trailing edge and return as traveling wave. The canopy, covered with indium tin oxide layer, has countermeasure to reduce the echo of the radar signal coming to its convex surface to the enemy radar. Surface material, geometrical shape, dimensions of the aircraft and also the wavelength of the incoming radar signal are effective in terms of absorbing and reflecting of radar energy. Based on our calculation and respecting to the countermeasure on KAAN Block 0, we can assume frontal aspect RCS as -20 dB SQM, 0.01 square meters. KAAN Block 1, with advanced magnetically coating and RAM panel layer, it could reach RCS value for X-band 10 GHz as -25 dB SQM, 0.003 square meters. ASELSAN X-band AESA radars on KAAN. Transmitter and receiver number of KAAN's ASELSAN nose radar, 2000. Gallium nitride semiconductor, liquid cooling. Range for RCS 1 square meter, target predicted 175 km with peak power min 40 kilowatts. Transmitter and receiver number of F-35s and /APG-81 radar, 1700. Gallium arsenide semiconductor, liquid cooling. Range for RCS 1 square meter, target 160 km with peak power min 25.5 kilowatts. Since the KAAN's nose radar is based on GaN semiconductor, it can be forecasted at least 5W more T/R power than the GAAS F-35's current radar and /APG-81. It has been accelerated prototype tests for the new radar N/APG-85 with KAAN processor, replacing the N/APG-81 used for the currently produced F-35s. 20 years ago designed, F-35s N/APG-81 radar falls behind the current technology. Assuming all other parameters are the same apart from emitting power rate, 40 kilowatts and 25.5 kilowatts, it corresponds to range 12% higher for KAAN's nose radar. So with a certain margin, safely, it can be assumed 175 kilometers for RCS 1 square meter targets. It's also considered that KAAN has X-band AESA radars on the side cheeks of nose and tail. It is expected that the KAAN will have wider radar coverage area than the F-22 and F-35. KAAN will be capable of jamming both frontal aspect with nose radar and rear aspect jamming with assuming X-band tail AESA radar. Rear-looking AESA radar feature of the KAAN will be unique and never will be available for F-22 and F-35 in case not using a pod, consequently higher RCS. Head-to-head engagement ranges of fighters with each other. While KAAN Block 0 has 17 kilometers, 9 nautical miles, disadvantage against the F-35A in the compounded effect of radar and RCS, when Block 1 KAAN's RCS improved to 0.003 square meters, minus 25 dBsqm, will be achieved the balance against the F-35 in head-to-head engagement. We remind again that the KAAN's assumption values in the calculation are taken into account the worst. KAAN is superior over 4th-gen fighters obviously even with Block 0 version. Also, Block 0 KAAN's IRST could perform a contribution to engage to F-35, has not IRST, beyond the 34 kilometers, means 17 nautical miles. KAAN's turbofan engine. Regarding to KAAN fighter jet, remarkable discussions focused on the turbofan engine. In Turkey, TEI, Turkish engine industry, is the only company that has the competence to design, test and produce domestic turbofans for KAAN, with the experience coming from design of TEI TF-6K/10K turbofan engines and the mass production and testing of the F-110GE variants. With the TF-6K/10K program, TEI will have experience in the small-scaled model of the TEI TF-35K in the transition for the KAAN's engine. Basic technologies and design choices, many sub-design parameters such as combustion chamber design, combustion chamber cooling technique, turbine blade alloy material selection, turbine inlet gas temperature limit and blade cooling technique, etc., and tests will be carried out on architecture of TEI TF-6K/10K engine. This model engine TEI TF-6K/10K will be taken as design practice reference. Experience and knowledge will be transferred to the TEI TF-35K, thereby accelerating the engine's transition to mass production for KAAN. F-110GE 129 turbofan engines have been used in the first lot prototypes of KAAN. When the engines in the chart compared among the 5th-generation fighters, it can be seen that the hottest is the F-135 turbofan engine of the F-35. The F-35's engine F-135 has 1,980 degrees Celsius turbine inlet temperature. It's necessary to use ceramic matrix composite CMC material to strength. However, while this high temperature is needed to reach demanded thrust level, but hot engine exhaust gas also increases thermal signature of aircraft significantly. To reduce the F-35's thermal signature, used additional cooling countermeasures that no other fighter aircraft required. As side effect of additional cooling system, it increases RCS especially at 6 and 12 o'clock due to geometric gaps. Responding the thrust demand with single engine for a 5th-gen fighter is giant mistake. It is necessary more fuel burnt in single engine means more thermal signature. In order to reduce RCS at 6 o'clock, the F-135 engine should not use additional cooling flow gaps around the nozzle, which we marked as the AB areas. Additional external cooling flow gaps around the mentioned nozzle reduce the thermal signature but increase RCS. KAAN's engines will not need any this kind of gaps for cooling air. The F-35 has internal air ducts as shown in the visual from under the wing, red dotted square, to around the nozzle. Ducts carry the natural air flow generated by the speed of the aircraft. airflow contacts with the rear housing hot surfaces of the engine. This is a cooling system that transfers engine heat to the air, so reduces the heat emitted by engine to the aircraft wing and fuselage. Air ducts cause cavity effect that will increase RCS at 12 o'clock. We think that air ducts had been added later to resolve heat signature problem. It was not possible to resolve this problem on the engine itself due to high turbine inlet temperature. KAAN does not need this under wing air ducts, also like F-22. While the exhaust gases pass from nozzle with chevron or sawtooth tip geometry, blends cold atmospheric air rapidly. There will be turbulent heat transfer from hot exhaust gases to air. This causes also energy loss, fuel consumption increases, with other words range decreases. With this turbulent heat transfer, nozzle heat signature is reduced. KAAN Turbofan TEI TF-23 will have chevron nozzle. F-35 has no super cruise, supersonic without afterburner, but dual-engine KAAN will have super cruise. The single-engine powered F-35 has to run constantly in hotter regime in order to generate demanded thrust. This hotter regime even brought peeling problem of ram panels of the F-35 in areas close to the engine nozzle. F-35 is restricted for a certain cruise speed and afterburner period. Contrarily, KAAN turbofan not needs to run into hot regime with high throttle level in order to fly supersonic. So, not necessary to have extra exhaust gas cooling countermeasure. KAAN's turbofan engine alternatives, prototype and mass production phases are shown in the chart. 20 KAAN, first production lot, will have F100 GE129 engines. Domestic TEI TF-35K will be introduced by 2030 or worst case 2032. It is natural that TEI TF-35K will use superalloy and single crystal turbine materials proven in the TEI TF-6K/10K engine. New technologies such as CMC, not yet produced in Turkey, will not be included. This is the right strategy. As can be seen in the chart, KAAN can produce much more lift force compared to its maximum takeoff weight due to its large wings. The load per wing surface of KAAN is 1,000 pounds per square meter. It is 65% of the F-35, 1,533 pounds per square meter. In other words, according to the equal lift force produced on 1 square meter of wing, if NACA indexes and flight speeds are considered equal on the wing of KAAN and F-35, the KAAN's wing will be loaded 65% less weight. This shows that the KAAN will be a much more agile aircraft in the turning maneuver and will be superior than F-35. It is almost equivalent to the F-22 in agility in turning maneuvers. However, since the F-22 has 2D thrust vectoring, F-22 will continue to be more advantageous. Chart indicates us, KAAN maintains maneuverability advantage over the F-35 even if it uses F-110 GE129 for prototypes and Block 0. Other sensors and futures of KAAN. In the future block versions of KAAN, electro-optical targeting system, EOTS, and forward-looking infrared search and track, IRST, will be used together. EOTS will detect objects on pilot's direction of sight and provide fusion with other images projected on the pilot helmet visor from optical sensors on the aircraft and will be used for marking and laser designation, also focusing the thermal images of the ground targets. Meanwhile, an IRST forward-looking infrared sensor, which is not available in the F-22 or F-35, will be included in the KAAN to provide situational awareness of aerial targets in the flight direction that are outside the pilot's line of sight and visual range. With this feature, the KAAN has more advanced architecture than the F-22 and F-35. In KAAN, modern design requirements such as autonomous airborne refueling and artificial intelligence-used emergency landing are planned in coming block versions. In summary, KAAN essentially will have 3 basic functions. 1. Radar stealth. Block 0 -20 dBsqm equals 0.01 square meters. Next block expected -25 dBsqm equals 0.003 square meters. 2. Powerful radar and weapon system. NOS AESA radar 175 kilometers, means 95 nautical miles, at 1 square meter target. Domestic air-to-air RF and imaging infrared missiles. 3. Flight performance. Super cruise. High climbing and turn rate performance. Conclusion. KAAN will be the cornerstone multi-role combat aircraft that will be in the Turkish Air Force inventory for approximately 50 years, starting from the 2030s, and will continue to be developed. Meanwhile, in the future versions of the KAAN, TUSAS will integrate high-energy weapons, principally laser, which are the requirement of the beyond 5th-generation fighter jet era, first as pod. Laser will be used against enemy missiles coming to KAAN in the first stage and in the destruction of enemy aircrafts in the next stage. With this new type of high-energy consuming weapon systems, the development of new generation and more powerful engines will be continued in parallel by TEI for the increased power requirement of the KAAN. Also, KAAN is able to be teaming drone command center and to make coordination in order to attack or defense missions with using domestic jet-powered drones, Stealth AN KA-3 air-to-ground and low observable Kiziloma air-to-air. Also, electronic warfare, electronic attack and more. All these explain that TUSA and its top management will be in a competition to maintain and increase the superior features of KAAN. Thanks for watching. You can find article link of this video in below. Please subscribe our channel to continue this type of videos.